This is our second video on circular motion. In this problem, you can see the picture, we have a rock of mass m, and it's being whirled in a vertical circle as opposed to a horizontal circle. A vertical circle means the mass is higher off the ground and then it's down close to the ground, and higher off the ground and then close to the ground, as opposed to a horizontal circle where the mass would be the same height above the ground all the time. The rope has a length L, and the stone has enough speed V at the top so as to keep the rope straight. And we want to derive an expression for the tension in the rope, which is a force. And you know what? Anytime we find forces, we always have to draw a free body diagram. So there's the mass right there. We know that it has a weight, m times g. Now, what about tension? Some students want to put tension pointing up here, but think about what that would mean. If the tension pushed up, that means that the rope would be pushing up. And ropes can't push. Ropes can only pull. And so there's a little bit of weirdness there. It takes a little thinking to get your mind around this. Ropes or cables or strings can only pull. They can't push. And if you're down here at the middle of this circle, right, if this is where your hand is, the only way that you can exert a force on this mass due to the rope is to yank down. See, if you're holding the rope here and you push your hand up, that isn't going to translate that force up to the mass. If you're down here and you want to exert a force via the tension of the rope, you have to be yanking downward. Now we use Newton's second law. The net force then, tension and mg are working as a team. So I'm going to add them up. See, they're working together. And that's equal to the mass times the acceleration. Whenever we have uniform circular motion, we've said that the acceleration is numerically equal to v squared divided by r. We're not going to derive that for you. Somebody else can do that if they want to. We're just going to take it at face value. Now, we need to be a little bit careful here because v is given, but it's not r that's given. I mean, the radius is given, but the variable that we're told is L. So we need to have L in our answer. We can't put R, because R, you can see, it's not given. It's L that's given. So we want to change that. All right, L we know, V we know M, G is a constant. So we should be able to solve this for the tension. Can we do that? Can I factor out an M? If I factor out an M, what does that leave us with? Isn't it v squared over L minus g? There we go. Notice that all of the variables on the right side of the equation are givens. Number 2, derive an expression for the speed the rock would have to have at the top for the rope to just begin to go slack. What does that mean? Doesn't that mean the tension would be 0? If we put a 0 in there for tension and solve it for V, what would that give us? Put a 0 there, the M just kind of disappears, and you end up with V squared over L is numerically equal to G, so the speed at which this rope is going to go slack is going to be equal to G times L, take the square root.